Hey, what's up, Chem peeps? Who is ready for some free response practice? I know there is nothing that I would rather be doing than this. Nothing. A student prepares a solution of potassium hydroxide for use in a titration experiment by dissolving 56.1 grams of potassium hydroxide in 100 milliliters of water. Part A. Show a numerical setup and calculate the molarity of the potassium hydroxide solution. My molarity equation, boom. If I need to calculate the molarity, I need to know number of moles and the liters of solution. Notice that we're told that we prepare 100 milliliters of this solution, or 0.100 liters of solution. So I've got the volume part done. Now I just need to know number of moles of potassium hydroxide. Gonna make you work for it. We're given 56.1 grams of potassium hydroxide. So to solve for molarity, I first need to convert my number of grams to moles. So I'm going to take my 56.1 grams, set up a conversion using dimensional analysis, keeping in mind that 1 mole of potassium hydroxide has a molar mass of 56.108 grams. Pulled that from my periodic table. Calculator time. 56.1 times 1, enter, divided by 56.108, enter. To 3 sig figs, I have 1.00 moles of KOH. Plug that back into my molarity equation. I have 1.00 moles in 0.100 liters. 1.00 divided by 0.100, enter. Oh, this is a concentrated solution. It's 10.0 molar. Boom. Be careful with your significant figures. Information related to the titration experiment is given in the table below. Boom. Notice some question marks. Bet we're going to have to figure those things out. In fact, we just determined the concentration of potassium hydroxide in the first step. We know that it's 10.0 molar. Just going to write that in to remind myself that I've already solved for that. Part B. Write the balanced chemical equation for the acid-base neutralization reaction between sulfuric acid, H2SO4, and potassium hydroxide. Alright, at this point, we haven't learned acid nomenclature, so we are given the formula for sulfuric acid, and we're reacting it with potassium hydroxide. Acid-base neutralization reaction, an example of a double replacement reaction. Recall that the hydrogen from the acid and the hydroxide from the base are to come together and form water, and the cation from the base and the anion from the acid are going to come together and form our salt. This time, potassium sulfate. Boom. Notice I focused on my nomenclature here. Always focus on the nomenclature first before you try and balance. Because sulfate has a 2- charge, I need 2 potassium here. Whew. Okay, now that we've gotten our formulas correct, let's balance this. I'm going to put a 2 here in order to balance my potassium, and then a 2 here to balance my hydrogen and my oxygen. Boom. Done. Part C. Show a numerical setup and calculate the concentration of the sulfuric acid. Alright, when we're looking for concentration, we're going to use molarity. So I'm coming back to this formula. I need to know moles of sulfuric acid and liters of sulfuric acid. Let's come back up here and take a look at our titration data. I know that I'm starting with a volume of sulfuric acid that's 12 milliliters. Boom. So I'm going to plug that into my molarity equation right away. Now I also need moles of sulfuric acid. As I come back up and take a look at my titration data, oh man, I'm not given any more information about the sulfuric acid. All I have is the volume that we started with. But I do know the volume and concentration of the potassium hydroxide I used, and I do have a balanced chemical equation. I'm going to use the molarity equation again. This time, I'm going to use it with my potassium hydroxide. I know the concentration of my potassium hydroxide is 10 molar, and I know that I used 36 milliliters of it. That's how much I added to completely neutralize all of the sulfuric acid. Let's jump to our calculator. 10.0 times 0.0360, enter. This means that I've added 0.360 moles of potassium hydroxide. Alright, now let's take a quick look at the balanced chemical equation that we just wrote up here in part B. The relationship between potassium hydroxide and sulfuric acid is a 2-to-1 relationship. So I can easily convert to moles of sulfuric acid using dimensional analysis. If I know that I reacted 0.360 moles of potassium hydroxide, and the relationship between potassium hydroxide and sulfuric acid is a 2-to-1 relationship, I know that my number of moles of sulfuric acid is 0.180. Now that I know the number of moles of sulfuric acid, I'm going to plug that back into my original molarity calculation. Divide by 0.0120. Answer 15 molar. That is the concentration of my H2SO4. Boom. So to recap, we took the concentration and volume of the potassium hydroxide and solved for moles of potassium hydroxide. We then used our balanced chemical equation to think about the relationship between potassium hydroxide and sulfuric acid. And we did that so that we could determine the number of moles of sulfuric acid. Because we were provided with the volume of sulfuric acid that we were originally given, we could then determine the molarity by dividing moles by volume of sulfuric acid. That brings us finally to part D. Potassium hydroxide is deliquescent and will readily absorb water from the atmosphere. If the sample of potassium hydroxide used by the student absorbed a substantial amount of water from the atmosphere during preparation of the solution, would the calculated concentration of sulfuric acid be greater than, less than, or equal to the actual concentration of sulfuric acid? Explain. Alright, for this one, I think first a quick visual to help you understand what's going on. Recall that from part A, we determined the concentration of the potassium hydroxide solution. And we did that by taking 56.1 grams and dissolving it in 100 milliliters to make our solution. So we determined number of moles. Boom. Which we calculated to three significant figures to be 1.00 moles. But imagine if some of that mass was actually water mass. And as you look at the balance on your right, I've placed some water molecules amongst the potassium hydroxide. So recognize that even though my balance reads 56.1, there's actually less potassium hydroxide than what I should have. So when I calculate my concentration, I should get 10 molar. That's what I'm going to calculate. So I'm going to calculate the concentration to be 10 molar, but in actuality, it should be less concentrated than that because I actually have less than 1 mole. Because some of that mass is water mass. So now let's think about the titration experiment. If I put my potassium hydroxide into a burette, I would expect it to be 10 molar or fairly concentrated, like this burette you see here. But it'll actually be less concentrated, again, because some of that original mass was water. So what does that mean when we perform the actual titration? Well, if it was all potassium hydroxide, let's say it would take it would take almost 30 mils of solution to neutralize my 12 mils of sulfuric acid. But in the example in which some of that potassium hydroxide was actually water mass, I'll be using the less concentrated potassium hydroxide. And so I'm going to use a greater volume. Let's say 50 mils. So as you think about part C in this step here, where we calculated the number of moles of potassium hydroxide we used, we're going to think that it's 10 molar, but we're going to use a much bigger volume than we should because it was a lot less concentrated than we thought it was. Which means that we're going to calculate a much larger number of moles of potassium hydroxide. And if we calculate a larger number of moles of potassium hydroxide, then when we determine our number of moles of sulfuric acid, that will also be larger. And if the numerator value in our molarity calculation is greater than what it should be, our concentration is going to go down because our volume of sulfuric acid is not going to change. Those 12 mils is going to stay 12 mils. A larger calculated number of moles of sulfuric acid in the same 12 milliliters would result in a smaller calculated concentration of H2SO4. Boom, and we are done.